This video is a presentation of the field trip we would have taken in Earth System history during spring 2020. I'm going to give you an overview of the northeastern Wisconsin geology told through the field trip stops that range from Precambrian near New London all the way through the Cambrian-Ordovician and Silurian over toward the east side of Green Bay. Let's get started. Here's a geologic map that shows the Wisconsin-Michigan region, the bedrock geology, and you can notice the bullseye structure of the Michigan Sedimentary Basin, outlined with a dashed red line. Nearby, both on the east side and west side, two arches of broadly anticline-like warped regional sedimentary strata exist at both the Algonquin-Findlay Arch over toward Ontario and Ohio, and the Wisconsin Arch trending through Madison and south central Wisconsin. To the south of Wisconsin is the Illinois Basin, and to the north and northwest we have Precambrian igneous, metamorphic, and metasedimentary rocks in northern Wisconsin, upper Michigan, and northern Minnesota. The red box shows the location of where the field trip stops are that I'm going to show you. The packet that you have that's available on Canvas allows you to do this trip, or almost all of the trip, on your own. They're essentially publicly accessible areas in most cases. Here's the bedrock geologic map published by the Wisconsin Geological Survey in the 1980s, and this shows sort of a striped pattern oriented southwest to northeast. The stripe pattern represents eastward dipping rock units of the Paleozoic that dip toward the center of the Michigan Basin. The only exception are the purple and blue rocks in the northwestern part of this map that represent parts of the batholith, the Wolf River batholith, and other Proterozoic aged rocks that are part of either the Pembine-Wausau terrain or part of the Yavapai terrain, as are the orange rocks in the southwestern part there. So there is one structure drawn in this map in Outagamie and Waupaca counties. It's a black line. It's representing a fault. I personally don't think it's really drawn in the right location. The map that they got this from is a little bit different in 1970, and I think that there's a lot of revision that could go on with this particular map. Anyway, what we're going to do is look at a subset of areas in here. What I've done here is I've shown the stratigraphic column on the right that goes from Precambrian all the way through the lower Paleozoic into the middle Paleozoic rocks of the Silurian. I'm not showing the Devonian here because those rocks are only exposed in the Sheboygan to Milwaukee area. So we're going to stick to Cambrian through Silurian for the Paleozoic section. The red boxes on here are most of the areas that I'm going to show you in the next several slides. We're going to start with stop number 2 because stop number 1 is usually at the Granite Company to give you an idea of what rocks can look like when they're large, cut, and polished and have all sorts of different structures in them. But to look at real rocks on the outcrop, we're going to have to explore this step by step. So section 2, or stop 2 over on the west, is in an area where there's a small Precambrian exposure called Cactus Rock. And at Cactus Rock, there actually are cacti there. There are cacti in all 50 states. But Cactus Rock shows an exposure of some Proterozoic granites, one of those little pink blobs there. 3, 4, and 5 are Cambrian and Ordovician sections. The 6A and 6B really represent early to middle Ordovician, and 7A through D represent mostly the Ordovician-Silurian contact. If you look at the entire section here, this cross-section, as you can see in the inset in the lower left, represents a northwest to southeast line of section. The vertical wells there, those are city wells or golf course wells on our campus and things like that. And this profile shows you that the rock layers are dipping eastward. It turns out they're about 20 to 40 feet per mile, with increasing rate of dip as you go to the east. Over on the Niagara Escarpment, we've got Silurian rocks covering Maquoketa Shale. The glaciers and rivers that preceded them exacerbated this difference in hardness of the rocks, giving you a Silurian rock that sticks up quite high. The dip slopes of the top of the Sinope group west of the escarpment and the top of the Silurian east of the escarpment form some pretty prominent regional drainage divides, especially in the Silurian for rivers like the Kewaunee, Onapee, and Neshota West Twin rivers that flow toward Lake Michigan. Over on the west, this part of the diagram is a little bit more schematic, and that's the recharge area for the confined aquifer system that flows underneath Green Bay. So for a lot of reasons, whether it's the history of deposition, whether it's the aquifer systems, or any other kind of public health related mineral driven chemical reactions that liberate arsenic or strontium or something, the geology sets the foundation for what we're looking at. And so let's look at some of these earliest rocks, the Precambrian. What I've done here is I've just repeated these, so you could pause this video. I'll give you a couple of seconds in case you want to find this again. I'm going to try to answer most of these questions as we go along, at least the ones that are easy for me to find photographs of that I had in my collection. So Cactus Rock is owned by St. Norbert College, and there's a turnoff area, and you can go and hike up the hill. There's a sign there, it shows you where it is. But I've given you latitude, longitudes for all of these points, assuming I did this correctly, and this will get you into the right spot. Well, here's what it looks like when you get to the top. There are lichens, those are the light green things there, sort of a symbiosis between algae and fungi, and they like to inhabit the rocks, especially igneous and metamorphic rocks. They get a lot of metals out of the surface, and they can get little tendrils in and really cover things up quite well. The rock itself is sort of that pink-orange kind of thing, and it's a very fine-grained granite. Here it's been polished by the glacier, and the thing running through the middle, up and down, those are fractures. Actually, they're a little bit of faults, I'll show you in a bit. And the thing running left to right is a quartz vein, and that quartz vein has been offset by those little faults. Let's look at how we know this was covered by a glacier, and something else about the age of this. When we look at this, you can see in the red box there's a pink blob. That represents the Precambrian. Now certainly we could have driven another half an hour west and gone to other exposures in the city of Wapaka and other places, but this one is pretty close to where we're going, and we can make a day of it by choosing these sites. These are Proterozoic granites that seem to be tied with the Pinokian origin, the Pembine-Wasa terrain, but as far as I know, these have not been dated. They tried to get zircons from them and were not successful. So it's unclear whether it's part of the Pembine-Wasa terrain or whether it's part of the Yavapai terrain. What does seem to be the case is that the orange rocks there in Waushara County and western Winnebago County, those are places like Berlin, Monticello, and Utley, and places like that. Montello, I should say, not Monticello. Montello. Those are places where the Yavapai terrain has granite and rhyolite that's about 1,760 million years old. The Pembine-Wasa terrain, as you know, is 1880 to 1830 million years old, and that's probably what these pink rocks represent here. The blue blob is the 1480 to 1520 terrain that's really not really terrain, it's more of the Wolf River batholith, an anorogenic granitoid complex of rocks, mostly granites and some anorthosites that have cut across a lot of the older terrains. Anyway, what we can see here is that we're dealing with an old sequence of rocks. Just to refresh your memory, what we have is the Archean Superior Continent in the north. That's older than 2.5 billion years old. There was a rifting event that laid down a lot of sandstone and dolomite, of the Kona dolomite and other kinds of things up here, about 2.2 to 2.3 billion years ago. And then an approaching island arc called the Pembine-Wasa terrain moved in from what's now the south, docked on here along the Niagara fault zone. So this is our crustal suture boundary here, folded and thrusted a lot of the rocks in here, and then there was also a back arc basin that developed up here. The Marshfield terrain sort of finished docking by about 1850 million years, and the final episode of granite intrusions and the maximum thermal event was at 1830 million years ago. Afterward, there was a lot of erosion, and another terrain docked in. That's the Yavapai province here. And the O'Plain Shear Zone here and the Spirit Lake Tectonic Zone, these are all representing suture zones between different terrains. The Yavapai province is mostly 1760 million year old rocks, and it docked around 1750 million years ago. And the Mazatzal orogeny follows the Baraboo Sandstone interval after the Yavapai Mountains were eroded, and then we ended up having a sand sheet deposited across the region. then a new mountain building event came and folded and metamorphosed those Baraboo quartzites. So when we look at this place here that's BS, that's the Baraboo syncline, that's also related to quartzites we find across northern Wisconsin, including the Barren quartzite in the northwest, Rib Mountain, Necedah Mound, and several others over at Waterloo as well. And those quartzites, for the most part, were deposited during the interval between the Yavapai and Mazatzal orogenies. When we go to Cactus Rock, we can see a nice, flat, smooth, polished surface. It's kind of difficult to see on here, but some of it contains nice, straight scratches, but it also contains these strange crescentic marks here. If you trace one of these fractures, you can see a very nice, thin little fracture curve. The concave direction is pointing to the right, in the direction that the pen is pointing, and that's how we read chatter marks to determine the unique flow direction of glaciers. There are other things called crescentic gouges that point the other way. They have kind of a three-dimensional character that looks different. But striations and chatter marks here can tell us the direction of glacial ice flow. When we look at the area that we would be visiting at Cactus Rock, you can see this is part of the Green Bay lobe of the glacier. The Green Bay lobe is traced out here, and the terminal moraine was reached about 18,000 years ago. The glacier melted, the margin melted back, and it re-advanced or had standstill events to produce each of these different moraines. What you can see is that there are places in Outagamie County and Waupaca County and even other areas to the north where not only did the glacier flow west, but in some cases it flowed northwest. Cactus Rock is one of these places that records both directions of movement, possibly during surges. And here's that evidence shown. You can see all across the upper part where the lichens are getting a foothold here, where these chatter marks have two distinct orientations. One that's sort of to the upper right, one that's mostly left to right, and down here there's another left to right. It turns out that these vary from southwest to slightly west-northwest when you take a compass and measure them. These chatter marks are produced when a boulder glued into the bottom of the ice sticks and then chatters or jumps across the surface of the rock with enough force that it's like a little jackhammer and it fractures this. You could imagine the same thing by taking a rock on a piece of glass plate or something where it could bounce and give you these kinds of crescentic fractures. So these are characteristic of glacial ice flow. This is a really interesting part of Cactus Rock. We don't know exactly how old it is, but we know it's probably Proterozoic. We think it's probably Pembine-Wasa terrain, but we don't know for sure. And we can put together a whole array of different sequence of events. We know there was an intrusion. There had to be a rock there that had intruded. We know that there was some sort of fracturing to produce this quartz vein. And then we had to have some sort of offset of that fracturing by some faulting. When these events took place is not entirely clear. Then we know we had this uplifted at the surface. There were all the Paleozoic rocks when the seas came in back and forth. And then much of those rocks were uplifted and eroded, and we end up seeing the glacial evidence here. So glaciers eroded all those rocks. Rivers before the glaciers eroded rocks too, and we're left with the final stage. So if you wanted to put this together as a story, a relative story, you'd be able to determine probably 6 or 7 or maybe even 8 distinctive events that have taken place that we can recognize on this outcrop. The next outcrop is a little bit farther to the southwest off of County W, and this is one that starts near the farthest in the base of the Paleozoic section that we can get. It's at the contact of the Cambrian and Ordovician section. So there's a pull-off area here near one of these quarries. Don't go in the quarry, it's private and it's posted no trespassing, but you can park on the road over here, and on the road itself you can look at the rocks in the right-of-way. And what you can see in this location is the top of the Jordan Sandstone, which is part of the Trempealeau group, and the base of the Oneota Formation. And there's a bunch of stuff that can be seen here. In this diagram, you can see the upper part of the quarry here, these rocks at the very back and back left. They were quarried quite a long time ago for dolomite to make aggregate for roads and concrete and things like that. And more recently, in the last decade, they were quarried for frac sand. where you sort out the quartz sand, and it's used for oil and gas well development after fracking as a proppant to keep the fractures open so that the shale becomes permeable after it's fractured. So let's look at what we might see on this outcrop. I'm going to show you some photographs from a couple of different places here. Both of them show, for the most part, the Prairie du Chien group and the structures that you're likely to see there. So over on the stratigraphic column, the Trempealeau group, specifically the Jordan Sandstone, which is most of the Trempealeau group in northeastern Wisconsin, that's shown in light yellow. And then in most places it's overlain by the Prairie du Chien group. Anywhere where it's exposed at the surface, it's overlain by the Prairie du Chien group at least. And notice the structures that are shown in here. There are G's in the Tunnel City group, which we won't see at this first outcrop. There is a little bit of dolomite here shown in the Trempealeau group, but mostly sand. And then this thing here is supposed to represent a stromatolite, and the little dot circles are ooids. And so we expect in both the base and sometimes at the top of the Prairie du Chien group, and also sometimes within, we should expect not only stromatolites and ooids in some places, but also sand layers. The layer in the middle of the Prairie du Chien group here represents a thin sand layer. On top of this, the dark blue Ensel group, we're going to address that a little bit later. So let's look at some of these things you would see in the red boxes. So we're moving up section, and the white quartz sandstone here is representing the Jordan. And this rock up here, this is sort of a tan dolomite, and it's got a lot of quartz in it, so that's the first part of the Ordovician. And we're really kind of recording a transgressive sequence here. As the seas came in, and the water deepens, the shoreline moves inland farther, we go from a clastic system with quartz sand to a carbonate system, which would have been limestone initially. It's been changed to dolomite now. And there are a couple of unusual features here, these little spherical things where things have weathered out. We don't really know exactly what they are. I think what they are small parts of the sand that were clumped together, and that sand rolled around on the bottom and was incorporated as a lag gravel, like little rounded off intraclasts. But it could be something else too. We don't really know exactly what it is. But at the end of the day, this is what the contact looks like. It's not always a perfectly straight line. And in fact, it turns out that there's alternating carbonate and sand up several meters up in this outcrop. One of the things you might see in many of the outcrops of quartz sandstone in Wisconsin, especially if you go to the castellated mounds over in the driftless area near Coloma and Roche Cree and places like that, those particular areas you might see the sandstone glistening in the sunlight. Especially on a really sunny day, you might see these bright reflections. If you do see that, close one eye and then close the other eye and look and see with one eye open. If it's only one of your eyes that has this glistening and not the other, and vice versa, that means that that's a glistening effect. This happens with snowflakes a lot of times in the wintertime in bright sun, but it also happens where individual sand grains have been overgrown by quartz crystals. And those quartz crystals have half-millimeter faces on them, and they're reflecting the direct sunlight back to your eye. But the patch of sunlight that's being reflected is so small that it's only hitting one of your two eyes, and that's what gives a glistening effect. Some of the things that we can also see, this is from a different location, are intraclasts. So these are some lithographic dolomite intraclasts surrounded in a quartz sand matrix. What this means is that we have kind of a tidal channel here. We've got currents ripping things up, we have stromatolites and ooids. All those things are characteristic of relatively shallow water systems. Here's some poorly developed stromatolites. I've got some better pictures coming up. But a lot of times wherever you have these little vugs, little pores that have had things dissolve out, you'll have crystals. So you can find crystals of calcite, quartz, galena, chalcopyrite, dolomite, fluorite, and a whole variety of other minerals that are instilled into these rocks or embedded in these rocks from fluids that once moved through them. Here are a couple of other stromatolites. This is a little bit larger, but you can see the arch shape to the stromatolite here and another arch shaped here. And the mottled color on here is different types of dolomite. Some of these rocks, if you hit them with a hammer, especially at the next stop, you can smell what smells kind of like diesel or hydrogen sulfide, a kind of a mixture of those things. And those gases are petroleum-related gases that have been included inside of the fluid inclusions in these minerals as they grew from a hydrothermal solution. This is a site a little bit closer to Shawano along Highway 29, but it kind of shows the same thing. This is the upper part of the Cambrian sandstone here, the Jordan, and this is the lower part of the Oneota with the intraclasts and stromatolites and ooids. So this is the Cambrian-Ordovician contact. Nearby to Gull Road is a quarry along Highway 45 and a fairly well-developed outcrop. This has been an outcrop for many decades, but it was enlarged about 20 years ago or so when they widened and moved Highway 45. I think it used to be County D or W, one of those two county roads. But now it's Highway 45 and they have a pretty decent outcrop here. And so what I'm going to show you are just a few examples of some of the things that you can see. Here's the overhead map of this, and the quarry owned by MCC is here. They're mining most of the dolomite for aggregate, but they do touch the top of the Cambrian sandstone. And the best place to look where you can park a car is over here on the east side of 45 in Outagamie County. It's posted over here not to go for Waupaca County, but there are some exposures here on this less well-traveled road as well. If you do park on a road like this, make sure your wheels are completely off the pavement. People are less likely to give you a hard time pulling off on the side of the road if you're completely off the pavement, if you can find a safe place for that. And then, stay off the road and make sure you are safe if you're near any cars. Okay, well, let's look at what we can see. We moved a little bit over here. This has kind of an unusual structure. If you look here, they've drawn a fault, but there's also kind of a straight contact here. It turns out that if you go over to Brown County, there's a fault that travels all the way through here. Dutton and Bradley mapped a fault in this area in 1970. I've mapped it and worked with people on seismic to map a fault in Green Bay. And T.C. Chamberlain mapped a fault in the 1870s over here in a slightly different area. And it turns out there's about 100 feet of uplift or offset along this fault. And that's probably why we have, although it's kind of hard to see, why we have this pink granite outlier juxtaposed right next to the dolomite. I think the fault goes right between these two, or a fault goes right between these two. The Precambrian is uplifted and the dolomite is dropped down. There's not much of an elevation difference between these two at all. It could also be due to some topography on the original topography of the Precambrian surface. That's definitely a case in many areas where you have what are truly islands. However, there's a lot of evidence for some significant faulting as you go all the way across this part. This is probably related to the Spirit Lake tectonic zone, and it's a paleoplate boundary, and there's been some small adjustment on this old plate boundary during the Paleozoic. So now we're going to look at some of the areas right about here in the lower part of the Prairie du Chien group. This is what a lot of the dolomite looks like. Much of it's muddy. It was probably a little bit farther offshore. There are some pods of shale and layers of shale in here. So it's not entirely all tidal channels. It's not entirely all stromatolites and ooids. Much of it is fine-grained dolomite that was probably more of a muddy limestone when it was deposited, and it's been changed after the fact. And you can see some interesting cross-cutting layers here. There may have been channels. Here's a layer that gets pinched out and sort of eroded away here. There are some interesting structures that you can see in here. I've found malachite even on this outcrop, which is a copper carbonate mineral, along with chalcopyrite and galena and even amethyst and smoky quartz. Here's one of these interesting cutoff layers. This was probably some sort of a subsea erosional event that cut off that layer, and then the next layer was deposited on top. Here it was again probably filling in a channel, and this layer up above, once that channel was filled, everything is more or less horizontal. So there's some interesting features that we can see that are sedimentary structures. Stromatolites are kind of abundant. I would ask that you not collect too many of these here. There aren't many left, and it's nice for people to be able to see this. But these Stromatolites are cyanobacterial mats that record shallow channel-like or tidal channel types of conditions here. And during the early Ordovician, there are lots and lots of stromatolites across Wisconsin and Michigan that have been recorded. We just don't have a lot of outcrops to be able to see this stuff. The lens caps are, again, they're for scale in here, just so you see how large this is. It's probably 5 or 6 centimeters or so across, but these are nice stromatolites. Ooids are also present, and in this particular case, most of the ooids are quartz cored. They're dolomite ooids, but the white ones here are places where the dolomite has been replaced by chert or silica at a very fine scale. And so the reason you get this sort of peppering of the white dots in there is that certain ooids were replaced by quartz or silica and others have not yet been. If we move on to the northeast a little bit near New London, usually one of the stops that we do right after lunch is the Mosquito Hill Nature Center. And this is a really interesting hike because it shows more of the Cambrian section with some really nice crossbedding, along with some interesting parts of the very lower part of the Ordovician Oniota Formation, that Prairie du Chien unit with stromatolites and ooids. So the Mosquito Hill Nature Center is northeast of the river here, and it's located within this red box. This box doesn't really have it mapped as anything other than Cambrian, but there is a very thin veneer of a Prairie du Chien on top of it. So we're looking at this particular part of the section. If you go to Mosquito Hill, you can park in the parking lot and you walk toward the hill. And when you get toward the hill on the path, bear left. It looks like you're going to go around the back side of it, but this is the best direction to go because there's a long switchback, and halfway up the hill, this outcrop, which is not a great outcrop, but it's pretty interesting, this is part of the Tunnel City group. The bottom part here is really weak. It's very weakly cemented, and it just falls apart. Try not to tear anything down here. It's a natural area. Even with this crusty cyanobacterian stuff on here, what I would ask that you do is pick up any of the loose material that's fallen. You can look at the things with your hand lens that way. Leave all the plants kind of do their thing. But this is a better cemented part of it, so it's sticking out as a shelf. But there are places in here with glauconite, that green mineral that represents fecal pellets in a stormy continental shelf. This is part of the Tunnel City group. At the top, there are lots and lots of sandstones. And I don't have all my pictures, I couldn't find everything, but these are some of the sandstones. And what you can see here is really nice bedding. Around the corner, a little bit farther up the hill, you can see really great cross bedding, especially when it's sort of sunny in the late afternoon and the shadows are just right. You can also see some mud cracks. In the person to the left here, there's an overhang. If you look up underneath that overhang, you can see some of the mud cracks. And there are a few little cross-bedding current ripple type things as well. If we move farther up section and we look at the St. Peter sandstone, which is the main unit in the Ansel group, that's this dark blue layer here, and the capping unit on top of that, which is the green Sinope group, you can't really see both of them very well here, so I'm going to show you the Piotr Sandpit, which is on private property, but it's still worth looking at here. And then there's a couple of other examples of things that you can see at the Velp Quarry and other places as well. So we're moving up now. We're looking at the contact between the blue and the green. So the Ansel group, mostly St. Peter, and the Platteville and Galena formations of the Sinope group. Still sort of middle Ordovician. Here's Piotr Sandpit, and what you can see is that it looks very white with a little bit of a rusty color to it in some areas. The white is just quartz sand, pure quartz sand. It's 99 point something percent SiO2 with very, very little accessory minerals. The only things you tend to find are oxide or sulfide mineral cements present in here. But this kind of material is used across the Fox Valley region, especially in Winnebago County. It's been used to make glass and for casting sands and some other things like that. When we look at this, again, we're looking at the dark blue layer. This St. Peter sandstone is interesting because after the transgression of the early part of the late Cambrian and the early Ordovician, that transgression stopped during the Ordovician, and we had a continent-wide regression, sea level fell, and a lot of incision of river valleys took place. So there's a really well-developed unconformity. It's not easy to see that unconformity in an outcrop in this part of the state, but what we do see is evidence of river valleys that are cut sometimes 300 or more feet deep through the Prairie du Chien group. There's a lot of karst and other stuff that's in the Prairie du Chien group, and then that entire thing has been filled in with sand. And so the St. Peter sandstone of the Ansel group, that dark blue, fills in the valleys and covers everything with a sheet of sand. Its thickness varies between 0 feet, where the Prairie du Chien and Sinope groups touch, all the way to a few hundred feet thick in some cases, like where I'm showing with the mouse, where the river valleys had cut down even through the Prairie du Chien into the Cambrian. We drilled through one of these in the Pulaski area in 2009 as part of a project we did. So here's what it looks like. This is very difficult to see many structures in. It's been fractured and broken up. I think there's some faults nearby, and that's why it's broken up a bit, but there's not much other than pure quartz, so it's hard to even see the original bedding. When we look at it under a thin section, the thin section shows you pure quartz sand. There are a few little sulfides and other things that are shown here. This one is not from the outcrop. Instead, this is from a drill hole underneath Green Bay. So this is from, I think, 199 feet or something like that underneath Green Bay from one of the drill cores that the Green Bay Water Utility took. But it's the same kind of thing. The blue here is, again, sort of an injected plastic just to show you where the pore space is, and the white grains are a couple hundred micron diameter quartz sand grains. Pretty well rounded overall. This makes for an excellent aquifer from a water quantity standpoint. But there are some challenges with water quality, and we can see some evidence on this outcrop. I can't easily get access to the quarry that's down the road that's a little bit farther down dip, but where you strip off the dolomite, it's full of sulfides, and that leads to all sorts of things like arsenic release and low pH waters and a bunch of other metals that give people a lot of headaches with water quality and public health. So some of these areas do show some interesting, more rusty areas, and these represent the oxidized remnants of hydrothermal sulfide mineralization that was present in this aquifer. It's most well developed at the very upper part of the St. Peter, up above where this quarry would have had its top, where the sandstone would have had its top. And the upper couple meters of the St. Peter tend to be mineralized the most. And we can still see some remnants of this sulfide mineralization. Here they are hematite concretions or other iron oxide minerals. These rusty circles are places that once housed or held pyrite. That pyrite has now oxidized and essentially moved away, and we're left with halos of these rusty materials. So it's kind of an interesting look. This is the oxidized part of the aquifer. This is the recharge area where the aquifer is unconfined. Going down dip is where you'd see it more confined. And that's a subject for hydrogeology or the groundwater class or geochemistry, where we can explore those concepts in more detail. A neat thing you can see at Piotr's Pit is a fault. And it's kind of hard at this distance to see it. You lose some of the perspective at the top here. But this brown layer in the middle of the outcrop over on the left side connects with the brown layer down here. And so this fault has the left side that's moved upward about a meter, or relative to the right side. The right side's moved down, left side's moved up, whatever it is. This is one of many pieces of evidence that shows that there's faulting in this area, and that's probably why, if we go back to here, that's possibly why we have some strange changes in the direction of the outcrop belt on this map. But that has not been worked out in great detail, and when Bruce Brown mapped Outagamie County, he did not distinctly map faults. Okay, above the St. Peter sandstone, or the Ansel group, is where we would find the Sinope group. Now the Sinope group is really well exposed in quarries, but it tends not to be all that well exposed in other parts of the Green Bay area. It's covered by a thin veneer of sediments from the glacier, but there are a few places where you can see this. This happens to be the Howard Quarry, the largest quarry near the county garages over here. This is where there's currently like a swimming hole and the scuba divers use it. It's flooded completely right now, but this is what it looked like about 20 years ago, right before they stopped quarrying, or after about 18 years ago. I think that's where it's starting to fill up with water here in 2002. So these two photographs are 18 to 20 years old, and you can see a very thick sequence of dolomite here. A little bit darker at the top where it's more shaly, but this is the Platteville at the bottom and the Galena dolomite at the top. Together, these two rock formations are about 200 feet thick, and probably 2/3 of this is represented here. This is essentially the dip slope. It's the part of the Sinope group that trends all the way down gently toward Green Bay as you move to the southeast. Well, I mentioned some of the sulfide mineralization that you see at the top of the Ansel group, but it's found throughout all of these rocks in northeastern Wisconsin. And because we would have seen this on our field trip, and you might be able to see this if you go out, anytime you see sulfide minerals like pyrite or the other sulfides, and many of these other crystals of things in these dolomites, what I want you to remember is that these rocks have seen some unusual fluids move through them. They've seen hot brines. The brines were at least 100 degrees Celsius, and the brines were 5 to 10 times saltier than seawater. And we know this by doing studies on fluid inclusions that are trapped inside of these minerals when they grow. That happens to be one of my specialties, and if anybody's interested in doing independent research related to this, I've got a fluid inclusion heating and freezing stage, and we can explore looking at what these minerals trapped and in further temperatures and actually measure the salinities directly by freezing them with liquid nitrogen. But it turns out that there are a couple parts of Wisconsin that are mineralized during the Paleozoic or afterward. The southwestern part of the state has the lead-zinc district that gives our name the Badger State because of the miners burrowing horizontally into the hillsides. This upper Mississippi Valley lead-zinc district is called Mississippi Valley type mineralization. The group of mineral deposits that's found around the world are typically carbonate hosted, and the type locality, really the place that it gets their name, Mississippi Valley, is this part of the Mississippi Valley in southwest Wisconsin, northeast Iowa, and northwestern Illinois. If you go to Galena, Illinois, it's named after the mineral galena that was there in this district. Eastern Wisconsin has a different type of sub-economic, none of this stuff's economic now, but sub-economic mineralization that includes complete dolomitization, changing limestone to dolomite, as well as a sulfide cement horizon at the top of the St. Peter Sandstone, and lots of other sulfides present throughout the carbonate section, especially in the Ordovician rocks. And the interpretation is that not only did it move from the center of the Michigan Basin westward, but there are others that have suggested that fluids have been expelled from the center of the basin and it moved radially out. My research focused mostly on flow from the basin out to the west. And so the rocks that we're looking at are over here. And when did this happen? We don't know exactly. That's ongoing research. We know some of the early potassium silicate mineralization like feldspars and illites that are grown from water. They're about 370 to 400 million years old. The calcites that are found in Green Lake County and some of the other places, they're about 190 to 200 million years old. And those are the last minerals in the stage of mineralization. So somewhere in between 370 and 200 is probably the age of the hydrothermal mineralization. But we don't know exactly what it was in timing and exactly what caused it. The Sinope group makes contact with the St. Peter Sandstone like this, and this is a heavily mineralized part of this. All of these rust spots here, that's places where the sulfides like pyrite and marcasite are weathering. And when you go into a quarry like this, you can just smell the sulfur in the rocks. And so sometimes they have some water chemistry problems as a result of weathering of these minerals on the outcrop. But ultimately, this is the contact here between the Ansel group and the Platteville dolomite. If we move on a little bit farther to the east, where we see the Niagara Escarpment and the Silurian rocks, this is where we can see some pretty interesting features at the contact between the Maquoketa Shale, and the Mayville dolomite, and sometimes the Nita ironstone. So I've got pictures from these 4 different distinct boxes here, and again, we're moving up section here. We're going to focus on this particular part. There are some places where you can see the middle part here, the Fort Atkinson. You can see that along the bay here by Green Bay, and you can also see it in places like Baird Creek over west of I-43, and also on the Ledgeview Golf Course. But we're going to focus on just the Silurian-Ordovician contact today. This contact forms an important geomorphological feature called the Niagara Escarpment. It's because of more resistant rocks on top of less resistant rocks like compacted mud or shale. These things form a cap rock that protects the shale. So if you think back to the Roadrunner and Wile E. Coyote and all of those rocks out in the western United States, the Colorado Plateau, you've got buttes and mesas. Well, those buttes and mesas are horizontally layered rocks, and you usually have limestones over shales. This is part of what's called a cuesta, and a cuesta is just a dipping mesa. It's just a place where the rock layers are tilted in one direction, and the cliff face is only on one side instead of being on both sides. And we have actually a number of escarpments. There's a little one here, there's a little one here. They're not really shown on this schematic diagram on the left here, but there are multiple escarpments. Even if you go to this escarpment up on Lake Superior, we call it pictured rocks. So it happens to be that all along the Door Peninsula and the Garden Peninsula in Michigan, all the way south down to Dodge County in Wisconsin, all the way east over to Ontario and New York, where we have Niagara Falls, this cliff face gives us some really cool scenery and beautiful waterfalls in the case of Niagara Falls. In our area, we have a couple of waterfalls that are in the same stratigraphic location. They include Kettle Falls, which is on private property, Fonferix Glen, and Weequahic Falls, and several others as well. There's one at Hilly Haven Golf Course and a few others. So let's look at what these show us. If we look at a zoomed-in view of the bedrock geology of Brown County, De Pere is over here near the Fox River. And where we're looking at is this area here. So this straight line, this razor straight line here, is the Niagara Escarpment over in East De Pere. This area right here where it sort of changes and you got this very strange thing, this is an old fault zone that's broken up these rocks, and Hilly Haven Golf Course is located right in here. And there's a cool waterfall right there. It goes over the escarpment. The escarpment kind of trends northward up here, and then it turns east. And so between several quarries that are up here, Fonferix Glen, and a couple of other places, all the way to I-43. I-43 is right here. This area here represents the Niagara Escarpment. Now it's probably turning east here because the rocks here are a little bit more broken up, and that's because of faults. These faults are mapped based upon limited rock exposures, but mostly based upon water well strata and the stratigraphy that we've been able to outline. So let's zoom in and see what we can see. If we zoom in a little bit closer, there are 3 different places. The one that's labeled here is Fonferix Glen, and that's a little bit upstream from the edge of the escarpment, but you can see the rocks right down at the end. And there's a quarry in here where these X's are. Those are my surface locations. And then this little notch is on private property, but I have a picture of it. It's Kettle Falls. I was able to get access a little over a decade ago, and this is one of the few places where the Nita ironstone is exposed at the surface in northeastern Wisconsin. This is basically the same view with an aerial photograph. Here's Kettle Falls. Here's the Ullman Quarry by Scott Construction. And this area here is Fonferix Glen County Park. Most of the photos I'm going to show you are Fonferix Glen. But this is the photo from Kettle Falls. I've got a postcard from right after the turn of the century in around 1908 or something like that. It's kind of a cool postcard. And this outcrop shows the Mayville Dolomite, which is Silurian, over the Maquoketa Shale, which is Ordovician, and then the Nita Ironstone, which has been called Ordovician or Silurian by multiple people. What's interesting is that this thing is controversial in its origin. People have been uncertain as whether it's bog iron or some other kind of subtidal or supertidal kind of feature. But ultimately, this is an oolitic iron formation, and all sorts of unusual chemistries and minerals are found in here. Phosphates, sulfides, oxides, and a bunch of interesting kinds of things that we see. Here it's about 5 feet thick, and I've drawn these yellow lines just so you can see the approximate positions here. The Maquoketa Shale has the Brainerd member, and the Mayville Dolomite is overlying this. At Fonfarks Glen, we can start downstream the farthest. This is the stratigraphically lowest part. There's some cool stuff here. There's a natural cliff face that collapses every once in a while. Be real careful here. There's a block that has rotated away and is sort of slumping down, riding on top of the soft shale. And if you go upstream, you can see a natural arch that's beautiful and eventually a waterfall. The waterfall was probably located over here at the edge of the Niagara Escarpment. But over an unknown length of time, whether it was just since the glaciers left here or whether this valley has been found between multiple glaciations, that's not entirely clear. But this couple 100-yard progression of the waterfall upstream is really the result of this cherty layer here. Less cherty dolomite at the top forms the cap of the waterfall, I'll show you. The weak part at the base of the waterfall is represented by this rubbly zone of cherty dolomite, and then this part here is actually what represents the base of the river valley near the waterfall. But here we've got this really interesting thing, and it's made for some interesting kind of features like natural arches. At the very base of this, you can see a little bit of the Maquoketa Shale. This green layer, which is mostly a carbonate-rich part of the shale, but it's full of sulfides and phosphatic layers. This is an unconformity for a couple reasons. One, it's an unconformity because the Nita ironstone is missing. But two, we have well-developed phosphate nodules, which are characteristic of non-deposition surfaces or unconformities a lot. And some of these phosphate nodules can be over an inch in diameter. I've seen some that are probably 3 or 4 centimeters long. Pretty interesting. Here's a view of the Maquoketa-Mayville contact, and these weird little brown things here are just slightly oxidized pyrite nodules that are in here. And this is a burrowed part of the Maquoketa Shale here and a burrowed part of the Mayville Dolomite. The base of the Mayville has lots and lots of burrows that are called thalassinoides, and I'll show you a sheet of one of these. And here's a different view looking up at the cliff face. This is a natural part of the cliff right along the edge of the river here. Bower Creek, I think, is its name. The cherty layers are usually stratigraphically bound here, and when we look at these, they're not just random nodules, there's actually a network of connections between these. It turns out that the chert probably occurred before the dolomite, because in many of these cherts you can see exquisite preservation of the limestone textures, shell fragments, intraclasts, and other kinds of things that are in there that are obliterated in the dolomite. So if dolomitization had occurred first, replacing the dolomite by chert would not have magically shown those fossils. But the chert replacement first preserved those fossil textures, and then the rest of the limestone was obliterated by the dolomitization process, and so you lose the textures only in the non-chert parts. Here's what one of the bedding plane surfaces looks like, and not at this location, but at some others in northeast Wisconsin, people have found trilobites inside of these preserved, and Joanne Klusendorf and Don Michalik have interpreted that these are probably or at least possibly trilobite burrows. And for one reason or another, whether it was permeability driven or maybe some other organic reason from something left behind, the chert and silicification preferentially occurs in these particular burrows. So you can see this contrast in this very robust, tight cliff-forming dolomite with a rubbly, really cruddy looking material here. The top part makes great aggregate. The quarry operators love this stuff. The stuff down here does not. It's got a lot of chert, it makes for bad concrete, and it also makes this thing kind of unstable. In here you can see honeycomb corals and chain corals, and here's a picture that I had handy of the stromatoporoid that's shown here. Sorry, I guess my text didn't get turned white on this particular one. But this stratigraphic column here, it's a little over 50 or 55 feet or something like that. Mostly the Mayville is represented with a little bit of the Maquoketa at the bottom and a little bit downstream. There's some really interesting corals and other things that can be found within the Maquoketa downstream. Syringopora is down there, and I think a couple of rugose corals as well. Other parts of northeast Wisconsin, this one's at the top of the road in Bayshore County Park. You can see all sorts of interesting feature. These horizontal, seemingly fracture systems actually turn out to be weathered stylolites. And stylolites, S-T-Y-L-O-L-I-T-E, stylolites are layers of insoluble residues, typically dominated by clays, and these things are produced by pressure solution and compaction of the carbonates. And so as a carbonate section gets buried by hundreds of meters or even kilometers of overlying rock, you can remove a lot of the carbonate by taking it away in solution. But the things that are not soluble, like quartz grains, maybe echinoderm fossils, and certainly clay minerals, are left behind sometimes as distinct layers that can be confused with shales, or sometimes like these from the same rock layer but in a drill core where it was cut and polished, wispy layers of anastomosing little segments of clay. This is the essence of stylolites. They're not depositional features necessarily, but it may look like they are on here. Some geologists have called this rippled laminated facies. These are not ripples, and they are not laminations. They are completely a diagenetic feature that has nothing to do with deposition. So diagenesis, the post-depositional processes, make a huge difference in what you end up seeing on the outcrop. If you're not careful, you can misinterpret things. So these are clearly subtidal, what we would call pack stones or even wacky stones. They are not shallow water carbonates by any means in the Mayville Formation. Back at Fonferric Glen, here's a beautiful natural arch. I think it's one of the neatest ones in the Midwest. There's one on Mackinac Island. There's one at Natural Bridge State Park down near Baraboo. But this one's really pretty cool. It occurs because we've got a robust dolomite at the top, a robust dolomite at the bottom, and this Churdy interval at Fonferric Glen that you can trace across the region as well is weak, and it has been sort of excavated away here. The old story was that there was a cow or a horse that poked its leg through here, and in the last 100 years or so, this has kind of opened up much farther. I've met people who say, yes, it was my family that had this happen, and it's a true story, so it's kind of interesting. If we go a little bit northeast of the UW Green Bay campus, we can see Wequiak Falls County Park, and here there's a nice progression from the Ordovician Maquoketa Shale, the Brainerd member. It has alternating dolomite and green shale, and then up here you have the Silurian Mayville, and the contact is not entirely obvious at this location exactly where it is. But this transition here also represents there's an unconformity in here somewhere. So Wequiak Falls is located at this location, and campus is right down here. The main part of the city of Green Bay is here. This is the Fox River. And Bayshore County Park, where I showed you the stylolites, that's located up in this spot. Downstream of Wequiak Falls, there's a pretty decent shale outcrop here, and this is also the Brainerd member of the Maquoketa Shale, but it's capped a little bit by some carbonates up here, but this is nearly pure shale. Very unusual fossils in here if you can find them, but this is my son Brian when he was much younger. So this is a cut bank of the Maquoketa Shale. Even farther up the road in Door County, right on Highway 57 north of the Door County-Kewaunee County line, you can see a large outcrop that's been cut when Highway 57 was widened. And on the north end of it, there's a nice exposure. It's a little bit overgrown now, but this is a nice exposure of the Maquoketa Shale with the Mayville Dolomite on top. So this is the Ordovician-Silurian contact, and it's an unconformity. Disconformity, specifically. So in summary, what I'd like to show you is an overview of what I've shown you on this virtual field trip. We started with 2 in the western part of the area where we saw the Precambrian. We moved through 3, 4, and 5 that showed something near the Cambrian-Ordovician contact. 6A and B showed you some elements of the Middle Ordovician, and especially 7A, B, C, and D show you the Ordovician to Silurian contact, sometimes with Anita, most of the time without. I hope this has been useful and interesting. Please contact me if you have any questions. I'm happy to answer them.